Okay, welcome to Math 349. So we're going to continue and finish off from Pascal to calculus, and then we're going to shift to how do you mean, which is one of the outreach topics. So I think when we last finished, we were able to calculate the derivative of a linear function and show that if the function is of the form cx plus d, then f prime of x equals c. And again, when you're teaching young students a subject like calculus, there is no need to deal with every function initially. You don't need to worry about the exponential, you don't need to worry about the logarithmic, you don't need to worry about trigonometric. Just try to do simple functions. And in fact, this inspires conversations on Taylor series. We understand simple functions, we understand polynomials. Can we try to approximate more general functions like that? Then, of course, there's also the trying to sniff out patterns. So we saw for linear function, cx plus d, the plus d doesn't matter at all, and the cx just becomes c. So we have a process. You give me a function, I give you a new function, the derivative. This is also an opportunity to talk about notation. F prime is wonderful notation because when you look at it, it's somehow related to f. That's what the prime means. Capital F over little f for the antiderivative. Okay, so now after the successful linear functions, it's actually not that bad to go and do a quadratic function. So I could do 3x squared plus 5x plus 2, and we can go through and we can do all the algebra, and I'll just jump a little bit, and we start expanding things out using the coefficients from Pascal's triangle. When you do it like this, however, the algebra is a little bit needlessly complicated. And you have to decide at what point do you want to prove various results. So how many of you have ever taken the derivative of x cubed? I think everybody at some point in their life has taken the derivative of x cubed. How many of you have ever taken the derivative of x to the 24,601? No one. Could you do that? Yes, because you know rules of differentiation. What if I gave you 1701 x to the 24,601? Yes. And so at some point you say, let's prove some rules so that we can take derivatives of compound functions simply in terms of derivatives of simpler ones. So we could have the sum rule. The derivative of a sum is the sum of the derivatives. Then we would never have to consider something of the form 3x squared plus 5x plus 2. We would just have three simpler functions and then combine them. Then you would do the constant rule, that if I multiply a function by a constant, the derivative is multiplied by a constant. So I would never have to do a 3x squared. I would just have to find what's the derivative of x squared and then multiply by 3. So if you spend a little time doing that, you never have to go through the algebra for a function like this. You would only have to do it for pure powers of x, x squared, x cubed, x to the 4th. And this is a nice way to motivate those rules from differentiation. There are infinitely many polynomials I can give you. But by using these rules, by spending some time proving these results in the beginning, it greatly reduces what we need to do. And so when we look through the algebra, we can see the Pascal's triangle coming in the different places. But it's really two problems. The x plus h, that's coming from what we did a moment ago when we did the linear function. The new one is the x plus h squared, which we're expanding out using Pascal. Okay, and so when we finish, we now see that the derivative is going to be 3x squared plus 5x. So it looks like the 3x squared, the 3x squared plus 5x plus 2 goes to 6x plus 5. And this suggests that maybe it's 3 times the power, and then the power gets decreased by 1 for the quadratic term. But it might be a little bit easier to see this if instead of looking at something like 3x squared, we just looked at x squared. And if we spend the time proving those rules initially. So again, when you're teaching, you have to decide what order do you want to do things. Do you remember when they proved things like the constant rule and the sum rule? Did you prove those first and then start looking at polynomials? Or did you do a bunch of polynomials? And then once you had that, did you then prove these rules to help you do more huge classes of functions all at once? This is one of the reasons why Calc 1 is an easy subject and Calc 2 is so difficult. I can't give you a derivative that you can't solve by just hacking away by using all these different results. But integration, much harder. So we can figure out what's going on. You could then ask your students, what would you guess would be the case of ax cubed? And they might even be able, if you haven't proven the sum rule or constant rule, they might even be able to guess these things right now. And if you think about a geometric interpretation of what's going on, does anybody here know special relativity? Okay, forget about it for now. So we will assume that we are in a non-special relativistic universe. If a train is traveling at 100 miles an hour and you're running at 10 miles an hour, which is a damn fine pace, I think, on the train, how fast do you look to somebody on the ground? 110 if you're running in the same direction as the train. 90 if you're running in the opposite direction that the train is moving. So speed is additive. So something like the sum rule for differentiation is very natural. And I have these different things contributing to my speed. Similarly, the rescaling rule, the constant rule, is natural. If I convert my speed, my distance from measuring things in yards to measuring things in feet, the numerical value has increased by a factor of 3. And thus, in those new units, it should look like I'm moving 3 times as fast. So you could ask, what would you guess for something like this? Well, we saw cx went to c. We saw bx squared went to 2bx. We might guess that ax cubed goes to 3ax squared. Okay, I'm going to skip all this. And then, one of the big questions, if you haven't seen this, is why do we care about stuff like this? And if your kids are not asking this question, then you really want to encourage them. There's a choice. There's only a finite amount of time in class. How many people have seen The Wizard of Oz? So my mother had never seen The Wizard of Oz except on TV when she was growing up. And she was much younger than her older sister, so she wasn't that much older than her niece and nephew. And she took them to the movies to see The Wizard of Oz once, and she was shocked because she had never seen it in color. She'd only seen it on black and white TVs when she was growing up. Most people have seen The Wizard of Oz. It's amazing to think which things survive from generation to generation. Why am I bringing this up? Which things should survive when we lecture? Which material should we still cover generation after generation? With the advent of computers, how you teach calculus has to change. When I was a kid, we had to learn how to use lookup tables. And how do you convert the integral you're given to something that's in the book? Because the book can't include every possible equivalent version. You had to learn techniques to convert to something that looks like a standard form that would hopefully be in the table. So over here, here's a great example of why we care. We can try to approximate a general function with what's going on locally. So the big idea of Calc 1 is that locally, any differentiable function looks like a straight line. Now, the longer you wait, the less likely it is that that straight line does a good job. But if you're traveling on the highway, if you look at your instantaneous speed, for the next 1/1000th of a second, you can predict quite well where you're going to be. Probably for the next second or two, but probably not for the next hour. And so if we look, the blue curve is our function, and the, we'll say, goldish function is the tangent line approximation at the point. And so one of the ways we can use this is we could try to figure out maybe where does the blue line hit the x-axis. I can approximate the blue line by the gold line and see where does it hit. Do you think this is going to be a perfect job? No, but it's going to give me a nice next try. And so the big question you want to ask yourself is, how good of an approximation is this? So what do you think might help us understand how good of an approximation this is? If you want to quantify this. Okay, but how would I do that? I mean, that would require me to know the values of the function. So what information about the function near the point 2 could tell me maybe how good of a job we're doing approximating? So basically, what information about the function at 2 might tell us how good of an approximation the straight line is? Well, okay, so the slope is going to give me the tangent line. And that's my approximation, but I want to know how close is that approximation to the function? At that point, yes, but I want to know if I move a little bit away from the tangent line, I want to try to estimate how much of an error am I making. So what information at that point would give us So what information do we use to get the tangent line? We have the value of the function, and what else do we have? The derivative at that point. So what else might help us figure out how good of an approximation this is? Well, we only have a function of one variable. The second derivative, right? If we now have the second derivative, that's the acceleration that tells us how fast the rate of change is changing. So if you have some bound on the second derivative near 2, then that gives you an idea of how much things can be changing. And then you can get upper and lower bounds. So if you wanted to make this exact, or if you want to have at least upper and lower bounds, say, I know I'm somewhere in this region, then all of a sudden, if you have information about the second derivative at the point, you can get information like that. You might need information about the second derivative more than just at a point, but maybe in some region. If I know the second derivative is bounded by 5, that can give me some information about how fast I can be accelerating or decelerating. Okay, how many of you have seen Newton's method? How many of you have not seen Newton's method? Has everybody voted? If you have not seen Newton's method, raise your hand. All right, more people have not seen Newton's method than have seen it, so I will try to do this quickly. If after this you do not want to be a mathematician, then talk to the dean of the faculty. I should be fired. All right. This is what converted me from I was torn between math and physics. And so much of math is about solving equations. If I give you, ax plus b equals 0, if you can't solve this, then you can go to the registrar and we'll kick you out. All right. Solving linear equations is not bad. Solving quadratic equations is not bad either. And there's a lot of different ways to do this. One of the ways is you do a successive sequence of equations. First, if there's no bx term, if there's no linear term, we just bring the c over, divide by a, take the square root. And then if there is a bx term, what we do is we translate. This is called completing the square, and we come up with something new, ax minus h squared. And we get rid of the linear term, and then it becomes easy. There are formulas for the cubic and the quartic, but if you go to degree 5 and higher, there's no longer closed form solutions. Just for completeness, here is the solution to the general cubic. All right. Did everybody memorize that? Can anybody give it back to me? Really, I had it on the screen for So obviously, no one wants to memorize this, and in the 21st century, you don't need to. But there are things you can do to make it a little bit easier. Can anybody give me a transformation that I could do to make this a little bit easier to work with? Instead of considering the cubic ax cubed plus bx squared plus cx plus d, you can say, without loss of generality, just study the following. What could I do? What related cubic would be easier to study? Without loss of generality, I can assume well, if I set C or D equal to 0, you need to be able to justify doing that. Before setting C or D equal to 0, there's another coefficient whose value you can determine without loss of generality. Without loss of generality, what? Which one is 1? Without loss of generality, A equals 1. If A is not equal to 1, then just divide through by A. And if A, there's only one time when you can't set A equal to 1. What's the one time you can't set A equal to 1? There's only one time I can't rescale and make A equals 1. Would be that one value of A. That's trouble. If A is 0, but if A is 0, this is not a cubic. Or it's a degenerate cubic, and we do not consider degenerate cubics as cubics for the purposes of solving the cubic. We would say, use the quadratic formula for that. So without loss of generality, we can assume A equals 1. And then once we have that, without loss of generality, we can actually translate and we can make B equals 0. So you could make the formula a little bit easier. And if you're lecturing, you could then go through and, I'm not going to do that, but you can see how much easier things would be if B is 0 and A is 1. How many terms would vanish? For completeness, those were the 3 solutions for the cubic. This is one solution for the quartic. What can we do for the quartic to make it easier? Yes, we could make A 1, and what else? So we can make A 1. So I can always translate. I can replace x with x minus h. And if you choose h appropriately, you can eliminate the quadratic term. So this is a nice little bit of algebra. It's very similar to completing the square. And so it's been a while since I've completed the square. Let's see if I can do this. So let's say I have a x squared plus bx plus c equals 0. Without loss of generality, will you let me just take a equals 1? I can just divide through by a. All right. Now, let's write x as, say, t plus h. I'm going to shift variables. I'm going to get t squared plus 2th plus h squared plus bt plus bh plus c equals 0. So I'm going to have t squared, and then what's my coefficient of my t term? I'm going to have a 2h plus b times t plus, I think it's going to be h squared plus bh plus c, my constant term. Have I done this correctly? I don't really care what the constant term is. What I really care about is, here is my coefficient of t. What should I take h to equal? I can take h to be anything. What should I take h to equal? Negative b over 2. Let's call this c prime, and then we would get, took too long and got a commercial. So then we would get t squared plus c prime equals 0. Can we solve t squared plus c prime equals 0? Yeah, we would get t equals plus or minus the square root of negative c prime. But x is just t plus h. So then we just add h to that. And we know what h is. H is just b over 2. So when you go through, this is how you get the quadratic formula. And you can see that what we're really doing is we're solving a simpler quadratic. What we're really solving is we're solving this quadratic. Once we know how to solve this one, putting in the linear term is not so bad. It's just a question of changing variables. So when we're looking at what's going on over here, I can always adjust x to kill the next highest power term. If it's a cubic, I can kill the x squared. If it's a quartic, I can kill the quadratic term. Sorry, if it's cubic, I can kill the quadratic term. If it's a quadratic, I can kill the linear term, and so on and so on. And now, for the quartic, I can kill the cubic term. So I could assume if I wanted to that a equals 1 and b equals 0, but you can see things are becoming a mess already. This is the solution. I'll just zoom in a little bit. This is just one of the 4 roots. But we do have explicit formulas. Now, let's say I give you a continuous function that's negative near 0 and positive near 1. What can you say about this? Why? Okay, what theorem? Intermediate value theorem. By the intermediate value theorem, I can't get from negative to positive without crossing. This is a really good way to find zeros. Now, in the intermediate value theorem, it's not constructive. I can't tell you where we cross. I can just tell you there must be a crossing. That's fine. That's enough for this to be useful. So what you typically do is you look at the halfway point. If the halfway point is 0, congratulations, you found the root. If it's not, if it's positive, then you know there's a root between 0 and 1/2. If it's negative, you know there's a root between 1/2 and 1. There could be many roots, but this will help you find at least one. So this is the method of divide and conquer. How many of you have seen divide and conquer to find roots, to find zeros? I've used this as games to entertain little kids. I can guess your birthday in 10 questions or less, but if I'm wrong, you have to say earlier or later. So can someone think of a day in the year? Doesn't have to be your birthday. Can someone think of a day? You got one. All right, is it January 1st? January 2nd? January 3rd? Am I an idiot right now? Yes, okay. There's no way to keep guessing like that. Is it July 1st? So all of a sudden, in that one guess, I've eliminated essentially 50%. July, August, September, October. Is it October 31st? And now with that next guess, I've eliminated. So each guess, I eliminate half of what's left over. And 2 to the 10th is 1024. So in 10 questions, I should be able to get any birthday. And I can even screw up once. And I don't have to be too careful about exactly where do I put the dividing line. So every guess cuts my uncertainty in half. That's wonderful. And so, if you want to, I could look at the function x squared minus 3. The roots are going to be plus or minus the square root of 3, which is about 1.732. And then if I apply divide and conquer, let's guess the root is somewhere between 1 and 2. Then if I look at f of 1, I get -2. If I look at f of 2, I get 1. So there's got to be a root between 1 and 2. So now I look at f of 1.5. F of 1.5 is negative. F of 2 is positive. So the root's got to be somewhere between 1.5 and 2. I look at f of 3/4. That's going to be positive. So the root is somewhere between 1.5 and 1.75. And so after 10 iterations, I have that the square root of 3 is somewhere between roughly 1.730 and 1.7324. And so, my value of square root of 3 is in that region. The problem is this is slow. So every 10 iterations, every iteration, I basically have my uncertainty. So if I do it 10 times, I get 1 over 2 to the 10. What's 2 to the 10? Which is approximately, we did this with Benford's law. 1024 is approximately 1,000. So essentially, every 10 iterations of divide and conquer give you 3 more decimal digits. All I need to do is evaluate my function and see is it positive or negative. I don't even need to evaluate the function perfectly. I just need to tell, is my function positive or negative? And every 10 iterations, I will gain 3 more decimal digits. That's not horrible. All right, now let's do Newton's method. And if you've never seen this before, this is one of the most remarkable algorithms I know of in mathematics. It is incredible how powerful this is and how far you can generalize this. And again, what this allows us to do is to quickly numerically approximate solutions. I don't want to numerically approximate solutions. I want to have closed form expressions. For example, anybody here doing economics? Okay, wouldn't it be wonderful if you could actually solve economic models and see the parameter dependence so that if you change the Federal Reserve rate or the tax rate or whatnot, you could see what that does to the economy? We can't do that. The models are too complex. There's too much going on. What you do is you do a tremendous amount of Monte Carlo simulations. And so you can't really see easily how these changes impact because you don't have closed form solutions that tell you as a function of the parameters, this is what you get. It would be wonderful if you had that. The quadratic formula, this is wonderful. If I increase the coefficient of A or B or C, I can see the impact that's going to have on my answer. That's wonderful. We don't have that in general. But if you don't have a closed form solution, at least this allows you to get to a solution. And so what Newton's method basically says is, look, take your function and make some initial guess for what you think the root is. Draw the tangent line, see where the tangent line hits. And if it's not 0 there, then have that as your new point and guess again and use the tangent line. So let me draw it. So for instance, let's say my initial guess is x0. So I draw the tangent line and I see where does the tangent line hit the x-axis, and I'll call that x1. And then if the function is not 0 there, then I play the game again at x1, and I draw the tangent line at x1. And when I do that, I guess I haven't, I didn't draw the tangent line again, I guess. Oh, well. Then when I draw the tangent line again, I would see where does that hit? And I keep going and going and going. So I guess I spent a little bit of time going through and trying to solve, for the equation of the tangent line. So let me just skip a little bit ahead, because you all know how to calculate tangent lines. And here we go. So here would be the next tangent line. Everybody here is comfortable doing tangent lines? All right, so in the interest of time, I'm not going to go through the math of how you would actually calculate the tangent line. But once you know the point and you know the slope, it's not so bad. Now we draw the tangent line at x1, and we see where that hits, and we call that in a shocker x2. And what do you think we should do now if this doesn't work? X3, right? Lather, rinse, repeat. You keep doing it again and again and again, and you keep seeing how far can it go. And so if we were to do that, we get 7/4 for x1. 7/4, right? That's 1.75. That's not bad if the answer is about 1.32, or 1.732. That's pretty close. So if we do it again, I'll just go straight to the table. And so here's the table. What's nice is it's always going to give us rational guesses. So we have 7/4, 97/56. My eyesight's not so good. 18,817 over 10,864. And so you can start to see how good of a job is it doing. And so what I did on the bottom is I wrote the square root of 3, and I wrote my 5th guess. And this is starting with my initial guess for the square root of 3 is 2. I hope we all agree that 2 is not an exceptionally good guess for the square root of 3. I'm not stacking the deck in my favor. After 5 iterations, look at how far you have to go before you finally see a digit that's different. This is some simple calculations I can do with a computer. I do not imagine that there is anything any of you are going to be doing in your life where you will need more than this much accuracy in the square root of 3. Probably even 18,817 over 10,864 might be enough. That's 1.732050810. Oops. And the answer is 1.732050807. So instead of 075, I have 100. I'm not off by that much. That might even be enough already for any purposes you'll ever do in your life. Compare this to divide and conquer. You divide and conquer. We had to do 10 iterations to gain 3 more digits. Essentially, every time you do Newton's method, you double the number of decimal digits of accuracy you have. Absolutely amazing. Why, on a philosophical level, do you think Newton's method does so much better than divide and conquer?
Because divide and conquer is just not using the information about the slope.
Good. So divide and conquer only needs the function to be continuous. Newton's method needs the function to be continuous and differentiable. It's not surprising that if I assume more, I can do more. This is the power of calculus. What's the disadvantage of Newton's method? You're assuming more. And so if your function is not differentiable, you can't use Newton's method. How many of you have taken probability or statistics? Okay, so how many of you have seen Chebyshev's inequality to bound probabilities? So Chebyshev says as long as you have your finite variance, you have the following bound. Well, this is great, but because this works for any distribution with finite variance, the bound is typically not that great because it has to work for such a large class. In many situations, you can use the central limit theorem and you can do a much better job of estimating probabilities, but you need to have a little bit more. And so there are some distributions that have finite second moments that have finite variances, but they have infinite third moments. And so you can't really do much better than Chebyshev. You can't actually invoke a central limit theorem type argument. So this is a really good point to be aware of, is what am I assuming? The more that I assume, hopefully the better I can do, but the cost is that it might decrease what it's applicable to. Most of the time, you may not care. Most of the time, you may say, okay, look, there'll be occasional situations where what I have does not apply, but most of the time it's going to be fine and I'm not going to worry about this. Anybody know my favorite sport? Or at least my favorite sport to mathematically analyze? Baseball. One of my favorite situations was years ago in the minor leagues. Can somebody define what a switch hitter is? Someone hits both lefty and righty. So a switch hitter faced a switch pitcher. This was somebody who could pitch with either his left or his right arm, and he had a special glove that he could flip. And so what happened was there was an infinite loop where the batter kept changing which side of the plate he stood on, and then the pitcher just kept changing which way he was going to pitch. Until finally the umpire said, "Your timeout. This is a minor league game. It doesn't really matter. Can you please just choose something for now, and we'll have Major League Baseball deal with this later. And now there's a whole elaborate procedure of what happens if a switch hitter faces a switch pitcher as to what happens. Most of the time, you're not going to have a switch hitter facing a switch pitcher, and you don't really need to be aware of that. And so if you don't know what the rule is, it's fine. The odds of you seeing something like that is so small, it's okay. But it's important that somebody knows what to do if that situation arises. It's very similar when we're developing mathematics like this. Most of the time, my function is going to be differentiable, and so knowing Newton's method is going to be enough for me to do a really good job. But there will be times when it's not differentiable, and I need to know what do I do in that case. Okay. There's just one fun example. As long as we're here, we've got a few minutes. I know some of you have already seen this part of the lecture, but I like this part. So let's take the function x squared minus 1. It should be pretty easy to find that the roots are +1 and -1. Now, if you go through the tangent line and do some algebra, you can actually get a really nice formula that says where is the next, guess towards the root from the previous. So if xn is your guess from the nth iteration, what is xn plus 1? As a nice exercise, go through and do this, and you'll see xn plus 1 is 1/2 xn plus 1 over xn. The 2 is because we're taking the square root. The 1 is the number that we're trying to solve. We're trying to solve x squared minus 1. If I gave you x squared minus 3, this would be a 3 here. If you think about this, this is reasonable. So let's say we're trying to calculate the square root of 3. So if we're trying to calculate the square root of 3, I'm claiming that the formula should be 1/2 xn plus 3 over xn. That will be my next value. If you were incredibly lucky, what would be the luckiest value of xn you could have in terms of trying to estimate the square root of 3? I'm sorry? Nope. There's only one number. What's the best number to try to get the square root of 3? Not 3. Nope. Nope. Doesn't have to be an integer, doesn't have to be irrational. Square root of 3, right? Imagine you happen to have xn equals the square root of 3. What happens when you put that in here? You get root 3 plus 3 over root 3. Oh, that's just 2 root 3 divided. It just stays the same. So once you hit the square root of 3, you stay at the square root of 3. This is a quick test to see, is this formula reasonable? Whenever you're teaching mathematics, whenever you're writing mathematics, especially expository mathematics, you always want to put in little checks. Is this answer reasonable? Is this formula reasonable for xn plus 1? Well, if I'm at the square root of 3, I would truly hope that my formula is not going to send me away. So this is saying once I'm at the square root of 3, I will stay there. Imagine I had a really bad guess for the square root of 3. Imagine I took xn to be, say, a large number, like 100. What would you say? What would approximately the next guess be? If I took xn as 100, what would approximately xn plus 1 be? About 50. The 3 over 100 is insignificant, so it's approximately 100. Would be, and then you take a half of that, so it would be 50. What would be the next guess after 50 approximately? 25, and after that approximately 12. So you can see it's falling very rapidly. What if I gave you 1 over 100? A very small guess. What would be the next guess? Yeah, it would basically become 150. You would overshoot, and then you would start to fall down. So it's kind of interesting. If you had 1 over 100, the next guess is going to be quite far away, but then you're going to start falling down very rapidly. So here's my question. Let's color the plane red if you converge to the root -1 under Newton's method, and blue if you converge to 1 under Newton's method. Which points do you think are going to get colored red? Which points do you think are going to get colored blue? Everything below 0 is going to converge to -1. And which do you think is going to get colored blue? everything. So there's one point that you've ignored. So this is our swing voter, the origin. Yeah, you're dividing by 0. We're not allowed to do that. So the origin does not go to either. And so you are correct. So every negative number under Newton's method will iterate to -1. Every positive will integrate to 1. So again, a lot of this is, if you go further, you want to prove stuff like this. If I have a method, I want to know, is it going to work? What root will it converge to? What this is telling us is, at least in this case, Newton's method has you converge to whichever root is closest to you. That's pretty good. So let's do a little bit more interesting example. If you've seen this before, don't speak up. So let's look at x cubed minus 1. So there are 3 roots to this. I could, of course, use the cubic formula, which I mentioned earlier. Nobody wants to use the cubic formula. Well, what I could do is sigh deeply, pray to the heavens, and ask, do you remember your polynomial long division? I'm not seeing anybody basically resisting the temptation to jump out of the chair with their arms raised. Me, call on me. Well, if I look at x cubed minus 1, if you look at this, there should be one value of x where if I put that in, this is clearly going to be 0. What would that x be? 1. So I know that this polynomial has to be divisible by the polynomial x minus 1. So I can do polynomial long division. And if I do polynomial long division, I get x cubed minus 1 is x minus 1, x squared plus x plus 1. If you don't remember polynomial long division, you can do the method of divine inspiration. And you can just say, I wonder if it happens to be x minus 1 times x squared plus x plus 1. And if you do that, you can see that it works out. If you don't know that, and again, when you're writing expository articles, it's not bad to give people, here's multiple things you could try. Does everyone agree that x cubed minus 1 is equal to x minus 1 times something? So I know it's going to be of the form ax squared plus bx plus c. And I just have to figure out what a, b, and c are. Can anybody tell me any of these values immediately? C has to be 1. And a has to be 1. And this comes by just looking at what happens when I multiply. And so now I know a equals 1, I know c equals 1. Now let me do the expansion and then figure out what b will be. And after the algebra, you'll get that b equals 1. So if you happen to remember polynomial long division, that's great. If you happen to remember the formula for the difference of 2 cubes, because again, I could write this as x cubed minus 1 cubed. And this is the difference of 2 cubes. At some point in your life, you might have been asked to remember the formulas for a cubed minus b cubed, how that factors. But as long as we know that x minus 1 has to be a factor, I can then say, look, it's x minus 1 times something. I know that something's got to be a quadratic. I can quickly pick off the x squared and the constant term coefficients. And now I only have to figure out the linear term. That's not so bad. All right, so continuing, I now have a quadratic. I can factor the quadratic, and I get 3 roots. 1, -1/2 plus I root 3 over 2, -1/2 minus I root 3 over 2. And so here are the 3 roots in the complex conjugate plane. And again, if you've seen this before, please don't speak up. There is a link to a YouTube video to watch the Newton fractal, which I'll let you do at home later. So now I have 3 points in the complex plane, and I want to apply Newton's method. So I send my guess xn to 1/2 xn plus 1 over xn. Which points do you think are colored green? Which points are colored red? Which points are colored blue? If you haven't seen this before, what would you guess? It's okay if you're wrong, but what would you guess? And if you don't know how to classify the entire complex plane, can you at least tell me some points that are red, some points that are blue, some points that are green? So one possibility might be x greater than 0. So why x greater than 0? So if I'm at 0, I'm equidistant from all the points. So why do you think x greater than 0 goes to blue? So is every point with x greater than 0 closest to blue? Only if y is 0. So maybe on the x-axis, all the positive numbers on the x-axis get colored blue. I can buy that. Can you give me a point that has positive x coordinate that's not closest to blue? Yeah, if I go to above and below one half. So I'm getting close to green. I mean, I would just take the point that's at the same y value as the green, the negative root 3 over 2. And if I'm like that, I'm going to be much closer to the green than I am to the blue. So can somebody give me a conjecture of how do you determine which point you go to? Can you give me like a nice English statement that a middle schooler could understand? Good. And then what do you do? Choose whichever's closest. So are there any points where we're going to have trouble? The origin, any other points? Yeah, if there are some points that are equidistant from 2 points, then we might have trouble. But except for those, which will be a set of measure 0. So basically, we would divide the plane up into 3 regions. And then all the points that are equidistant, we would have trouble in terms of where they go to. But everything else, we should have a red region, a blue region, and a green region. If you actually do the calculation, you get a fractal. So this is Newton's fractal. It's an absolutely remarkable shape. And again, you can watch the video, and it's going to zoom in nicely on all of this. What I love is we're starting with a really simple problem. Trying to find roots of functions. Roots of quadratics weren't too bad. Roots of cubics, we do have a closed form expression. If we try to use Newton's method, all of a sudden, this should pain you. You're over here, I'm closest to the blue root, but depending on where I am, it's extremely sensitive to initial conditions. If I change ever so slightly where I am, I could all of a sudden be going towards the green or towards the red. If you look down over here in the negative x-axis, all of these points here are going to blue. But we've actually seen something like that before. We saw the point 1 over 100 jump to 150 as the next guess. And so unfortunately, this algorithm can push you quite far, and then you could get captured by a different point. So again, we're going to do more in this class than is going to make it into any expository paper. Part of this is to just get some things on your mind. This might make it into the book. This might make it into future classes. This might make it into your professional career. Be aware of the consequences of what you're doing. Try to get a sense of what's going to happen as we actually iterate and do stuff like this. How sensitive are things? I can share this story because I do not know the names of any of the people involved other than my father. So he was taking an MBA class from an extremely theoretical professor who gave them an equation involving 46 variables to describe what their company should do in any business situation. Like myself, my father is a nice, good, studious person who would never think of making trouble for anybody, always polite. And he calmly raised his hand, and he might have said something along the following. I don't even know the values of these parameters for my own company, let alone for my competition. How am I going to use this formula? But isn't it a beautiful formula? And that's when my father learned to just smile and nod. Yes, it's a beautiful formula, and this will be on the test. Okay, got it. Completely useless. Now, for a lot of things, you just need to get a sense of how well do I need to understand something. And there are some values that are extremely important, and there are other values that are not that important. If I have a pendulum, how many equilibrium points does a pendulum have? I'm sorry? 2. What are the 2? So pendulum is, something, a pendulum bob swinging. So no, those aren't equilibrium points. Just if I leave the pendulum like this, it's not going to move. What are the two configurations for pendulum, which will be at equilibrium? Straight down. Any other equilibrium? Straight up. One of them is stable. If I change this by just a little bit, if I give it a small push, it's not going to change that much where it is. So if I change the value of theta from 0 by a small amount, there's very little change. Up here, however, if I change it by a little bit, all of a sudden it's going to go all the way around that. And so if I'm at the equilibrium that's straight up, this is extremely sensitive. If it's not exactly straight up, if it's just a little bit off, it's going to have a wild motion. And so if you don't know the value exactly, you could have wildly different behavior very quickly. If you're straight down and you're off by a little bit, okay, it might be oscillating a small amount, but it's not going to really be changing that much. So in terms of trying to figure out which values do we need to know and how well do we need to know them, if it's the straight down versus the straight up, very different situation. I have a former student who has done a lot of work on climate change. And I do not want to get into the politics of climate change. I will say he's looked at some of the climate models, and some of the model predictions are extremely sensitive to small changes of parameters. This does not mean the conclusions that people are saying are wrong. It just means you have to be really sure that, if this theory is correct, that you have the correct values for these parameters, that very small changes can lead to wildly different behavior. This is one of the lessons over here. When we are coming up with these algorithms from calculus, the fact that this has so much instability that if you change the values just a little bit, you go to a wildly different answer is extremely important. And so when you're trying to figure out, which methods and algorithms you want to use, this is something to be extremely aware of. Right. So there's a lot more you can say on fractal sets. It turns out that there is a fractal structure in Pascal's triangle. And so if anybody's interested, let me know, and I can send you some stuff about the fractal structure in Pascal's triangle. Not surprisingly, all math is related. But what we saw in these, two lectures is, we start off with some really simple concepts, trying to expand numbers, expand polynomials. We got from this to calculus. And then since we still have, I think, about a minute and a half left, okay, so if I gave you x squared, we know its derivative is, yeah, it was really sad, guys. I gave you x to the 3/2, what's its derivative? And if I gave you x to the root 2, right? Now, what the hell does it mean to raise x to the root 2 power? If I want to do the derivative of x to the 3/2, I can't use Pascal's triangle. I don't know what x plus h to the 3/2 is. So there's a fun problem to think about is, how would you actually calculate the derivative of x plus h to the 3/2 minus x to the 3/2 over h? How would you actually calculate this? And if you can do this, then do the harder one where you replace the 3/2 with the square root of 2. How would you actually calculate that? You all got the answer right, okay? You all know your basic calculus. But the question is, did you actually see a proof of this in your calculus class? Or is this something that the teacher slipped by you? So think about for next class, how would you actually calculate the derivative of x to the 3/2? I know two ways to do this using simple techniques. X to the root 2 is a little bit harder. All right, so this is a good place to stop.